my dear students, and welcome to another session for this physics class. And for today's topic, I'll be discussing the electric charge and the electric force. Now, by the end of this lesson, you must able to know and to learn how does this electron and protons are observed. And also, by the end of this lesson, you must able to know how to use the Coulomb's law. Now, without further ado, allow me to proceed to the next slide. Now, please take note that positive and negative charges are always measured in coulombs. So, at this point, coulombs will be discussed in the later part, but now I'll be discussing how does the positive and negative charges works. So, before that, allow me to give you a brief introduction about the modes of the atom. First, if you observe in this illustration, you got the Greek model, Dalton model, Thomson's Plodding model, Rutherford's model, Bohr's model, and the quantum mechanical model by Schrödinger. Now, in the Greek model in 400 BC, this was proposed by Democritus. So, for Democritus, for him, he believed that an atom is just simply a circle, indestructible, and a very small unit. Now, in 1800, for Dalton, he also used the idea of Democritus, but this time, he considered this model as a billiard ball. So, just imagine this one is a billiard ball. So with that, it gives an idea, or okay, let's say that they got the picture of idea that the atom model is just simply a circle or like a ball. Okay. Now, yes, again, this is still indestructible, but nothing on it, just simply a ball. Now, for in 1897. With the idea of Dalton, Thomson's come up with an idea of a plum pudding. So if you will observe in a plum pudding, allow me to illustrate that. So example, this is the plum pudding. Here's a plate. Okay. And then you got the cherry on top. And you got the glaze. So for Thomson's, these raisins that you will see here, or the toppings, okay, it serves as the protons and electrons that are inside on the atom. Okay? And with that, Thomson's come up with a concept that in every atom, there is a composition of different subparticles such as neutron, protons, and neutrons. Okay? Now, with that, Rutherford also used again this model of Thomson by defying the electrons. So the electrons, as you can see, because Rutherford believes that in every atom contains positive charges, nothing more, nothing less. For Thomson, it's just simply electrons are just everywhere, but he didn't focus to that. Okay? He didn't give more emphasization about that in every atom that has a electrons, but it's simply subparticles, the protons. Now, for Rutherford, for him to able to prove that in every atom, if there's a positive, there's always a negative. So he used the method of gold foil. The gold foil method. So here, the gold foil method, okay, so example, you got this device which emit a gamma rays, okay, where here there is a gold foil surrounded by a steel sheet. Okay, so with this steel sheet, whatever deflects onto that, it represents that there is a representation, or let's say there's a visibility of the electrons. Okay, now, moreover, in 1913, Bohr is a student of Rutherford. So he used the idea again of Rutherford's, but this time Bohr created a new model. But this time, if you will observe, this model represent as or imitate the solar system. That is why, again, for Bohr's, if again, if he believes that the center of this one is the sun, which contains atoms and neutrons. Now, the surrounding planets for Bohr's, according to him, serve as the electrons that are orbiting around the atom. Okay, and with that, with our present time in the quantum mechanical model, this by proposed by Schrödinger. Schrödinger. Okay, so Schrödinger believes that atoms are everywhere. So atoms cannot be seen by our naked eye, but eventually it can be seen only with the use of microscopic device or equipment for us to see the behavior of the electrons. He proposed so many studies, such as the parting in the box, how the electrons behave, the double slit experiment, so on and so forth, where with this quantum mechanical model represents that electrons cannot be contained, cannot be observed, and then again, atoms are in everywhere. Okay, and that is the all brief history of these models of the atom. Moving forward to that, if we're going to study or read this one, The Origin of Electricity, it says is that electrical has a nature of matter and it inherent in atomic structure. So again, we have the electron, which has a negative sign, proton has a positive sign, and the neutron, which is served as the neutral charge, or let's say no charge at all. Now, as this electricity originate, so here are the different characteristics in terms of their weight and in their charges. So for the mass of protons, it has a 1.673 times 10 raised to negative 27 kilograms. Mass of the neutron is 1.675 times 10 to raised to negative 27 kilograms, and the mass of electrons is equals to 9.11 times 10 raised to negative 31 kilograms. Okay, so that is their weight, and under to this one, the protons and the electrons has a constant charge of positive 1.60 times 10 raised to negative 19 coulomb. So again, the C here that we are talking about is the coulombs. Now, don't worry, later again, I'll be discussing how to use coulombs and what is coulombs. But right now, let us focus on the constant charges of these protons and electrons, which has a 1.60 times 10 raised to negative 19 coulombs. Okay? Now, please take note that atoms and electrical has a neutrality in terms of their equal number. So again, if you have a 6 protons of a certain element, and therefore it has also a 6 electrons, again, they should be equal. Okay, now here in the net electric charge, this helps us to determine how does the electric charge of a certain atom increase its charges or decreases its charges. Okay, now with the use of this formula, the Q serve as the net electric charge, E serve as the charge of an electron, and N serve as the number of electrons added or removed. So eventually, the N here will be constant because it can be positive or negative, because it just focuses if how many was being added or how many was being removed, regardless if it is positive or negative. Now, in the charge of electron, will help us determine if can be positive or negative, which is same also in the net electric charge. The result may be positive or negative. It may varies on the problems or the solutions that we may encounter. Okay, so just like this one example, how many electrons are there in one column of negative charge? So if you will observe, okay, in this problem, we have already a question here. Okay, it says here that how many electrons are there in one column. Okay, how many? So if we're going back here again in our formula, or in this definition of this formula, number of electrons added or removed. Going back again on the problem, says here that how many electrons are there. So we can assume that how many does a certain atom contained, okay, or how many electrons have been added or removed. Again, it can be positive or negative. That's why it will be absolute. Now, using this formula, for you to easily remember it, you may use this pyramid where Q is our net charge, N is the number of added or removed electrons, and E will be the electron charge. That is why, if we're going to apply this formula, we use this. N is equals to Q, or the net charge, divided by the charge, the electron charge. Okay? So, our net charge you consider as the one column because it says here in our given. And then for our E, okay, we can use 1.60 times 10 raised to negative 19 column. Again, it can be, regardless if it is positive or negative, it will become absolute. Okay? And with that, we just simply substitute everything for us to get the 6.25 times 10 raised to 18. Okay? Do we need to put the unit? Don't need anymore because it's just simply asking how many electrons are there. Okay? It's just the number of electrons. We're not referring for the charge. Okay? Now, because any electric charge occurs in integer multiples of elementary, the indivisible charge of magnitude, electric charge is said to be quantized. What do you mean by quantized? When you say quantized or quantization of electric charge, it means just it is only a finite set of discrete values. It means that no matter what, how many times you multiply or divide this number, it should be end up with the same charge of either positive or negative 1.60 times 10 raised to negative 19 coulomb. Okay, so again, it says here that the charge is an integral multiple of the charge of an electron. Okay, so it means that, again, discrete values. So example, 1.60 times 10 to negative 19 coulomb times 2, then you'll get the answer, times 3, times 4, times 5, up to what? Up to 100. Even up to 100, again, if you divide that, still it should be visible by 1.60 times 10 raised to negative 19, and that is quantized. Okay, it was been limited. Okay, you're not getting a small charges of it. You're not adding a small charges of it. It means that it is a constant. It is a as is. The as is amount was being what? Divide, multiply, divide, multiply. You're not getting that, like example, 1.59, 1.58, or let's say 0.26 times 10 raised to negative. That is not considered as quantized. Okay? So that will be another story for that. And please take note that in every charge of a neutron, there is always a zero coulombs. Why? Because all the neutrons are always in neutral. Zero. Okay? Now, for these questions, allow me to give you a run through, and also let's try to answer it. Okay, and as we answer the following questions, and allow me to give a briefly explanation for you to have a more understanding about this one. Okay, now example of one, a brass key has a net positive charge of positive 1.92 times 10 raised to negative 19 coulomb. Approximately, how many electrons must be added to the key to make it electrically neutral? Okay? If we're going to analyze of this problem, you see it says here that how many electrons? So, we got the hint that this question is considering is the number of electrons or the charge has been added or removed. Okay, now do we have an electric charge? Yes, it already says here the net positive charge will be 1.92 times 10 raised to negative 19 coulomb. Okay, so this will be our net charge, and what will be our electron charge? Yes, it's either of these two will be our E. And with that, what formula we're going to use? Okay, so the formula we're going to use is N is equals to Q over E. You're getting it? Now, let us all substitute all the values in this formula. So N is equals to 1.92 times 10 to negative 16 coulomb over 1.60 times 10 raised to negative 19 coulomb. So we put that in a calculator, and what we will get here is 1,200. Did you get it? Now, if you think this discussion is very fast, you can take a screenshot or take a pause and then try to solve it on your own. Okay? Now, let us now proceed. Next question is, can an object carry a charge of 2.4 times 10 to negative 19 coulombs? Is it A? Yes, if the object is a conductor. B? Yes, if the object has electrons or protons. C? Yes, if the object is an insulator. D? No, because objects do not have charge. Or E? No, because charge is quantized. Okay, so if you're going to think of this one, and you still have a little background in terms of quantizing the net charge, you may answer of the following this. It can be A, B, C, right? Because you're just simply answering by a yes or no. But if you're going to analyze in a term of carrying a charge of 2.4 times 10 to negative 19 coulomb, the questions will be what? No, the answer will be no. Because the charge is quantized, it means that nothing change. Nothing varies. Okay? It was been quantized. So, that is 2.4 times 10 to negative 16 coulomb. So, again, an object cannot be carry a charge of 2.4. It should be as is. What will be the charge of itself? Should be always what? 1.60. That this 1.60 times 10 to negative 19 coulomb, this is the only charge of a certain object can carry because of the protons and electrons. That now, more than that, let's say 1.621, that will be wrong, or 2.24 such as this one, or you go lesser to this one, then therefore it not be alive, because again all the charges of the protons and electrons are always quantized. Okay, now next, the smallest charge on a single particle has been measured to be 1.60 times 10 to negative 19 coulomb. What can we conclude from the fact that no smaller charges have been measured, but multiples of this charge have been measured? Okay, if you're going back again in my discussion in my previous slides, what do you mean by quantization? Okay, can you define it on your own? What do you mean by quantization? Okay, and now go back to this question and then try to understand it more. Okay, read further. So and look for the clues. So for the clues is here is that it said that no smaller charges have been measured. However, okay, or but multiples of this charge has been measured. Ano ba yung multiple of charge? Ito po yun. No? That is the 1.60 times 10 to negative 19 column. So it means that the charge itself is as is. More and more, divide, multiply, divide, multiply. I didn't take any small amount of it. No small amount was been added, but just simply as is charge. So therefore, the answer will be what? Okay, the charge will be quantized because it's only discrete values and it's multiple of 1.60. 1.6 times 2 times 3 times 4 times 5, so on and so forth. Now if you're going to say 1.60 plus 2 plus 3 plus 4 plus 5 minus 2 minus 3 minus 4 minus 5, then therefore that will not be considered as quantized charge. Okay, because you add and you remove. But if you're going to divide, you multiply, divide, and multiply by its own charges, then therefore this 1.60 times 10 negative 19 column of a charge of protons, electrons is considered as quantized. Okay? And that will be the end of the first discussion of in terms of electric field and electric force. On the next video, I'll be discussing, which is also related to electric field and electric force. But this time, I'll give you a background or a knowledge regarding about the charging through induction and conduction. And let's try to experiment that. And let's see if you yourself can generate an electricity. Okay? And with that, thank you and see you again on my next video.